You probably already know that computer programs are not written in English or in any other spoken language. In this lesson, you'll learn why, and a little bit more about how a computer receives and processes instructions to run a program. So here are some of the basics about languages that we've already covered. We've already covered that in the programming process, we use languages to write our algorithm. We've looked at a little bit of visual and text-based languages, and we've briefly touched on the concept of high-level versus low-level languages. And in this lesson, we will focus on building on those topics. So the definition of language for computer scientists is a vocabulary and a set of grammatical rules for instructing a computer or computing device to perform specific tasks. And of course, remember that in the programming process, languages are used to write the code. So how do these programming languages compare to other spoken languages that we're familiar with? English, French, Italian, Chinese, Arabic, Hebrew. These are languages that grew around human communication, and they have both written and spoken forms. And the formality can be specific, can be different. You might speak one way to a friend, you might speak another way to your grandmother or to your boss. The attributes of natural languages that you see on the screen, you'll find are similar to computing languages. So the question is, why wouldn't we use natural language if that's what humans are fluent in? It's what we think in, it's what we speak in, it's what we write in. Why wouldn't we use those to write computer programs? And the problem lies in the fact that natural languages can be ambiguous, which means they can be unclear, or phrases can have multiple meanings, and you have to rely on context or your understanding of the person to know which meaning was intended. Computers need clear, precise instructions so that they execute exactly as intended. So let's take a look at an example of how human language, natural language, could be ambiguous. Imagine that this were a newspaper headline: "Bear attacks man with sandwich." Just think about that for a moment and try to picture what this newspaper story is really about. Did you think of a picture? All right, let's see if your picture matched this. Did you picture a man who had a sandwich and who for some reason was attacked by a bear out of the clear blue sky? So did you picture the man having a sandwich? Or did you picture something a little more like this? The bear was actually the one who had the sandwich, and the bear with the sandwich attacked the man. The bear used the sandwich. Somehow it was a very dangerous sandwich, and the bear decided to attack the man with it. Both of these are funny, and these are silly examples, but if I click back to the first slide and we look at the sentence, or it's not really a sentence, but the headline, we can see that it really could have meant either one. We don't know because of the way this was constructed. We just don't know who had the sandwich. Natural languages develop gradually over time and typically informally among whole societies. But programming languages are artificial languages, and they're typically developed by small groups for a very specific purpose. Typically, they are going to be much more simple and structured than natural language. Artificial languages designed for programming include Java, C++, Swift, Python, BASIC. Some older programming languages would be Pascal, COBOL, Fortran. But what all of these have in common is that they use a certain set of keywords and punctuation in order for the programmer to express an instruction in a form that can be interpreted and executed by the computer without any question, without any ambiguity. Here are a few examples of the varying syntax between different programming languages. Just to print the word hello, or to show the word hello on the screen, might be written in each language. And you'll notice, without even knowing the language or what all of the special symbols, punctuation might mean, that each of these statements is fairly understandable to anyone who speaks English. Yeah, by the way, many of these keywords in programming languages do tend to be English as opposed to another natural language. The first example is in Python, and we can see the command print is stated. There are parentheses, there are quotation marks around the word hello. That actually is pretty consistent. We can see that any of these that we look at actually all have that in common. They do have the word hello in quotation marks and that string in parentheses. We'll revisit textual programming languages later on in Unit 4 when we look at digital media processing, and you'll get to try your hand at writing programs in the Python programming language. The reason we're using Scratch in this course is that textual programming languages require us to learn syntax, very precise and exact spelling, capitalization, punctuation, and all of that. And those things are usually specific to the language. In this course, we're really trying to wrap our minds around the bigger concepts of computational thinking. So focusing on little syntax rules like where to put a semicolon won't serve your learning for the AP exam. Visual and block-based programming tools automatically handle all of that grammar and syntax that the programming languages require. And it allows us to focus on the logic of the program rather than the syntax. The block of code that you can see here shows how individual programming blocks can be assembled in a language like Scratch. A wide range of languages exist, both natural and artificial. Ultimately, language is a tool for communicating an idea. And in the case of computing, this communication may be with other humans, or with a machine, or anywhere in between. And in the middle of this, remember, we have a software program called a compiler to serve as the interpreter for us. Because, as we'll find out, things don't necessarily translate easily one to another. A high-level language is going to be platform independent. In other words, a high-level language program can be understood by a PC or a Mac, an iPhone or an Android. And again, the key feature of these high-level languages is that there is a lot of abstraction that has been done to allow humans to really understand this language as well. Some examples of high-level languages would be Scratch and Python, both of which we use in this course. And you can see an algorithm to assign the value of 2 plus 3 to a variable x. And you can see both ways that you are going to see something like that in this course. Now, on the other end of the spectrum, low-level languages are completely dependent on the underlying hardware. The language that the computer uses is very specific to whatever processor is inside the machine. So there's a direct correlation between the ones and zeros of binary and the billions of microscopic electronic switches that are embedded into the circuitry of the processor. Remember, it's a little software program called a compiler that turns high-level code into low-level code so that the computer can understand. So low-level languages are optimized for machines. Computers are built using highly structured circuitry that responds to logical and clear signals. Because low-level languages are much more concrete and straightforward with a limited vocabulary and a very structured syntax, nothing is left to misinterpretation. This table is in the lesson, and you can certainly refer back to the lesson for more detail about this. But this table shows the spectrum of high-level to low-level languages, basically with natural language being at the highest level and machine language being at the lowest level. The bottom level here, the low level, is the least abstract. It's the most concrete because it is the most specific to the computer's hardware. There's no way to misinterpret a 1 or a 0. So there is very little abstraction. This table shows the different way that things can be expressed in the different types of languages. And if I asked you, and I didn't tell you what this was, and I said, hey, try and figure out what that does, that would be a little difficult. And so you can see that there's very little abstraction. There's nothing left to question for the computer. It's either a 1 or a 0. It's an on or an off. Then we move up to low-level programming language, and a language like assembly language that is a little easier to understand. If we look right here, I can see LD. Not quite sure what that is, but I could take some guesses. And, spoiler alert, it's short for load. And I can see the word add. And so that I know that word. And so I can tell that there has something to do with adding, loading, and storing going on. Now, I don't know exactly what the other stuff means, but I also recognize the quantity 2 and 3 and the letter X. So that's a little bit easier to read because there's a little more abstraction, but not much. It is still not very clear to me what that means. Now we get to high-level programming. So here's where we do have quite a bit more abstraction. Over here, I can read these things. This is a mathematical looking statement. I can pretty much guess what that is, and I can look at those scratch blocks and I can see that we are setting X to the sum of 2 plus 3. So again, that one, humans can understand it if you think about it for 2 seconds, but the computer can also understand it. So there's a little bit of abstraction, but not so much that the computer would misinterpret what we mean. At the very, very top, coming in first on the abstraction scale, is this sentence written entirely in English. It's a pretty clear sentence. I, as a human being and an English speaker, can read that sentence and know exactly what it means. However, a computer might have a little bit of trouble. It is not specific enough for a computer to be able to follow, but it is the highest level of abstraction.